I'm going live here. What is an angle?
Where two lines meet at a point.
Two lines meet at a point, yeah? If we take two lines meet at a point.
You have complementary angles there.
That's a point. Two lines meet at a point. Two lines don't meet at an angle.
It's the portion of a circle. It's the portion of a circle that is between the two lines.
Is the portion of the circle where what?
It'd be like the, I like the, maybe the angle would be the portion of the circle.
We're getting somewhere. Raise?
It's just an angle. Like,
An angle is just an angle. And let's think about, shh, Jackson. Let's think about this. It's a very simple question. What is an angle? It's just an angle. We know right here is an angle. It's not math? Well, no. We know when we're looking at an angle. Right here is an angle. But how do we define it? Well, can we do it without measuring something? We've got a right idea here. Between two lines, well, if I have two lines, how do we have a degree measure between those two?
intersecting. Yeah.
So what we're going to do to define an angle, and here's where I'm building this up from the beginning. We need to understand the vocabulary the same. An angle is not the intersection. An angle is the amount of rotation. This is how we get through it. It's the amount of rotation.
Aren't you still measuring something?
It doesn't need a measure. We don't need a number. So there is a rotation between it. It's the amount of rotation between, I'm going to say, two rays. I wrote that wrong. Two rays that share a common starting point. And we remember back to geometry what it means to be a ray. We have a start and we have a direction. So if we have a ray, we have a common starting point, and a ray goes off indefinitely in one direction. Another ray can go off indefinitely in a different direction. The angle is not the intersection, is not the point. The angle is not the lines, the rays themselves. The angle is the amount of rotation from one ray to the next. It's how much space is between. Now, be careful with the word space, because space usually means area or volume, but that amount of rotation between one to the other. That's our angle in there. Now, with the angle, some other verbs, other words that we have. That point that the two rays share in common, what do we call that? That is our vertex. It is that point share in common. I'm going to make an exact copy of this angle. It's about the same? Close enough? I'm going to say those two angles are not the same.
How do you know?
Those two angles are not the same.
Why do you say that?
What's different between my two diagrams there?
They're rotating different.
It's the rotation, it's the direction of the rotation. What I have here is my arrow is rotating counterclockwise. Here I have my arrow is rotating clockwise. So it's all about the start as well. Now this starting side, we call this the initial side. It's the initial side of an angle, where the rotation begins. So here, on the one on the right, this would be our initial side. We are rotating clockwise, we are rotating counterclockwise. So we've got initial side is the starting side from which the angle rotates, and then we've got terminal side. Terminal side is the side where the angle ends. So far, so good. Now, we've mentioned that, okay, we've got an angle. It's that how much rotation, or it's the rotation, so direction as well as the quantity of rotation. So once we start measuring it, then we can put some numbers to it. Now, we know that we measure angles in terms of degrees. What do we know about degrees? Important degree measures. 360 degrees. What's 360 degrees? 360 degrees is one circle, is one full rotation. Because we're talking about, back to the amount of rotation. So 360 degrees is one full rotation. So I'm going to step aside for a moment. We have my trig chucks. That's what they're called. That's what it says. Trig chucks, like trigonometry and nunchucks combined. So, Jackson, I'm going to hit you with something. It's on recording, so everybody else is going to know. So, here I've got initial side is written on one side. Terminal side is written on the other side. So our angle is that amount of rotation from our initial side to our terminal side. Let's just eyeball some things. If we have, our angle starts here, and we rotate all the way over here, what do we have? 360 degrees. It's that amount of rotation. It's that amount of rotation. So we have one full rotation, 360 degrees. I'm going to go back. Half a rotation, 180 degrees. Okay. Quarter of a rotation, 90 degrees. Okay. So rotating through, we've got 90 degrees. We've got 180 degrees. What angle is that? 270 degrees. 270 degrees. It looks like 90 degrees. It looks like 90 degrees. If I hold it like this, it looks like 90 degrees. If I hold it like this, it looks like 90 degrees. But how much rotation have we actually gone through? From here, we've already passed 90. We're still rotating in the same direction. We're up to 270 degrees. It's 3/4 of the way around. So Jackson, what angle is that?
270?
No.
You see, he went the other way.
So, let's start again. Bit of tightness. Let's start again. So everybody's watching. What angle is that? 270. What angle is that?
Oh, 90. There you go.
Almost. Almost.
45?
That's 45.
Yeah.
So once again, what angle is that? 270.
Oh, it's negative 90.
It's going to be negative 90.
Oh.
Give me out.
It's all about the rotation. It's all about the rotation. If we go on a number line, we can go in one direction. If we go the opposite way in a number line, we have negative numbers. So what we have here, if we have counterclockwise rotation, counterclockwise rotation is a positive angle. Whereas if we have a clockwise rotation, the red marker's okay, yes?
It's the best.
Well, I'm just making certain we can all see it.
It's the goat.
If we have clockwise rotation, it's going to be a negative angle. And it's going in the opposite direction. So opposite direction, opposite value. And so it does matter in which direction we rotate. Going back, I had this one, positive angle, negative angle. It makes sense that counterclockwise is positive, right? Let's go back and make sense out of things.
Quadrant 1, 2, 3, 4.
Exactly. And where did that come from?
Aristotle.
Oh, I don't know about that. No, the quadrants go back to Rene Descartes. Same guy. Back to 6th grade. Back to 6th grade, or whenever. Your 6th grade teacher said, here's a coordinate plane. This is X, this is Y. We're going to call this quadrant 1. And everybody in the room said, no, we read left to right. This one should be quadrant 1. And the teacher said, no, this is quadrant 1. Okay. Then you say, this is quadrant 2. No. What quadrant's down here? 4. This is quadrant 4. So I'm using Q to represent quadrant. That's quadrant 4. We use Roman numerals. That's the standard way of writing quadrants. We go quadrant 1. We have quadrant 2. We have quadrant 3. Quadrant 4. And it moves counterclockwise. Now, inevitably, somebody back in 6th grade got a little bit ahead of things, and they said, but teacher, why does it go 1, 2, 3, 4 backwards? The teacher said, I don't know, just deal with it. Just suck it up. That's the way it is. Well, it goes actually trig. It goes to trigonometry, how we measure the angles. We started off talking, okay, this is positive rotation right at the start. This is the positive rotation. This is how we begin. This is going to be negative rotation. So the quadrants are opening up in the positive direction.
They easily could have done it the other way, though.
They could have, but we always start here. We start here, and if we start on the, we start in quadrant 1 because everything's positive in quadrant 1. X is positive, Y is positive. And I'll get into something standard position.
But then why does our clock go negative?
That's a good question.
Why do they do that?
I don't have an answer for that. Bonus points, bonus points if you can figure that out. Bonus points on your test grades if you can figure out, if you look up for why the clock goes clockwise. Because it'd be really hard to call it a counterclock. Sure. Bonus points, go. Oh, that might be it.
Figured it out.
I think it goes with a sundial. I think it goes with a sundial. Brilliant.
Who thought of that?
All right, Courtney.
Oh, okay.
You're really something else over there.
Thanks, Jackson.
Standard position of an angle.
Yeah. Chemical clocks were invented in the northern hemisphere by inventors who were trying to make models of the sun's movement in the sky.
Okay. That works then. So, standard position, an angle on the coordinate plane. So I can put this onto a coordinate plane, onto a graph, so that we can start seeing things. With our initial side. The positive x-axis. You can read that. An angle on the coordinate plane with initial side on the positive x-axis. So this is typically how we're going to look at it. And when we start talking analytical trigonometry, graphing this so that we can see everything on a plane. Here, start on the positive x-axis, we rotate all the way around, we would have 360 degrees. Here's my stumper. If we start on the positive x-axis, and we rotate that far to the negative y-axis, we just said that was 270 degrees, right? On the other hand, if we start at the positive x-axis and rotate down, what was that angle? It is negative 90. So direction matters. Think about this. If you have a car, if you have a bike, if the tires rotate 90 degrees in one way, it is different from rotating 270 degrees in the opposite way. Your car would end up forwards or backwards. It would not end up in the same location. Now, on the graph, negative 90 and 270 both end at the negative y-axis. We've got two angles that end in the same place. We're going to call this coterminal angles. Get this definition down. Coterminal angles, along with everything else. Because quiz, test, exam time, when I say find the coterminal angles, and you say, oh, I don't know what the word means, it's here. A lot of this is vocabulary. So coterminal angles. Third quarter, spring semester, fresh start. That's why we're doing it this way. Coterminal angles. Angles that share a terminal side.
I don't need to write that down.
I'm going to remember that.
Coterminal angles are angles that share the same side. That's what co means.
If you can make sense out of the language, yeah.
Oh, I cannot wait for the test. Give me that question number 1.
Question number 1 is usually change between degrees, minutes, seconds, and decimal degrees.
Yeah, I probably know how to do that.
You better. How many minutes in an hour?
60, I believe.
Okay. If I give you 1.25 hours, how many minutes is that?
It's going to be 75.
Okay. That's the first question off the test. Simplified, of course. It's the idea of coterminal angles. All right, we got this. So watch. What's our angle? 90. What's our angle? Negative 270. Looks the same. So actually, you got to reset there. Now we're reset. There's a little counter on the back that tells me how many rotations we've gone through. So if we go here and then here, where are we at? We have 450. How do we get 450? Just to simplify it out. We go one full rotation, 360 plus another 90. What's the biggest angle we can have? It's the smallest angle we can have. We can go negative. We can have any angle in here. So if I take this and I just go and I spin it around a bunch of times, you know what? You're going to get hurt and I'm going to laugh at you. So we spin it around a bunch of times. What's our angle?
A lot. 360 times.
What was it?
360 times the amount of.
So we could take that basic angle and we could add 360 degrees times however many rotations. Let me fix my notation in here.
Is that a theta?
That is a Greek letter theta. So if we have, and I will indicate it like this, we can do this. We say, okay, there's 1 rotation, 2 rotation, 3 rotation, so forth. K is the number of rotations. The letter on front, the circle with a line through it. That is the Greek letter theta. Greek letter theta is what we use for our angle measure. So we can find coterminal angles just by adding or subtracting rotations. Cosine theta. The theta, just to put it here. Yep. A lot of angles, angle terminology, typically we use Greek letters. So this is the variable for an angle measure. Mu alpha theta? Yeah. So far, so good? Now, I'm gonna